Benadryl. But you didn't. You're just leaving me out to dry. And Sham is there for me.
You should tag me in the video.
All right. If you haven't noticed yet, I've been taking your names out when I say them. All right. Let's just start over again. Okay, so for our cut, redo, next time I'll just accept the error. All right, so our first example, we're going to be hanging a picture. We brought a new mirror home. It's 20 pounds, and I have decided, just to make life easy, put a couple of nails on the wall and just hang it in the fashion that you see here. How many pounds of force do each of those wires need to support?
10 pounds each.
Oh my gosh, 10 pounds each, right off the top of your head. 10 pounds on each of those cables. And hopefully they're just, not barely strong enough, but over-engineered and can hold a lot more than that. But each of those cables are going to support 10 pounds of weight. How many vectors are up here? Everybody in chorus. 3, not 2, but there's 3. There is a vector V. There's a vector V. And in component form, maybe I'll do this. We have 3 ways of writing vectors in component form. There's A times vector I plus B times vector J, a notation I really, really do not like, which means that for this notation, what do we have? 0 times vector I plus 10 times vector J. No horizontal movement, just a force in a vertical direction of 10 for 10 pounds. And we have the notation that I like the best. We have vector V is equal to 0, 10 in component form. We have vector U, which is going to represent the force, basically being exerted, if you will, or applied to this wire. And in component form, since there's no horizontal movement from the initial point and we're going up 10 units, a length of 10 to represent that magnitude of U being 10, that length of that vector, that directed line segment equals the force that is applied in the specific question. So we have vector U in component form is 0, 10, but I only see 2 wires. Where's the third vector? It's the vector representing what? The gravity, the force, the weight of the picture itself. So there is a third vector that I'm just going to start here, and it's going down, except that's going to run me through the 20. Well, it'll be through the middle, but there's a third vector going down, which we'll call vector W. It's going to be twice as long as each vector V and U if you're drawing it to scale, because that mirror weighs 20 pounds and it's getting pulled down vertically by gravity. So you have vector W that's in component form. There's no horizontal force here. It's just getting, so the A component is 0 and your vertical component is negative 20. If this picture is hanging static on the wall, as we hope it does and doesn't come crashing down, these 3 vectors are said to be in equilibrium. What do you think equilibrium means?
They balance each other out.
Meaning that when you add those 3 vectors, you get... So vectors that are in equilibrium are vectors that add up to 0. Anytime you have an object in space, you're in your chair. You have weight pushing down on that chair that is supporting you, vertically, so you're sitting still and not rising or falling against the, on the floor. A crane holding something up in space, unless that is, if that object is holding still, that object is in equilibrium, there are forces that are working together to give a sum of 0. When you look at our 3 vectors and add them up, vector V plus vector U plus vector W is 0 plus 0 plus 0, kind of boring, but I'm just kind of teaching a concept. Then we have vertical components of 10 and 10, so we have 10 plus 10. Adding our last third vertical component, we have negative 20, and the sum of these three vectors, of course, is 0, 0. If those did not balance out, that picture is either for some reason moving up, left, right, or obviously what would happen would be something would snap and this thing would fall to the ground. So let's talk about these cables snapping. So I come up with this idea. I want to make it easy. A couple little strips of cable, 2 nails on the wall, hang the frame. Okay, wife's like, I don't want to see the cable. Okay, I don't want to see that on the wall. I want it to look nice. I'm not that modern, you know. I want this thing hanging on the wall and the cable and the nail, the anchor, behind the mirror. We don't want to see it. So I'm going to draw the diagram so we can actually have something to look at. Because I don't know physics, I'm going to say that there's 2 wires, but more than likely in the real world it's actually just one that's hanging over a nail. But we got, again, 2 wires, but they're coming together and they're hanging on a single nail. And I have used a length that will allow and this is exaggerated, I want a 10-degree angle on that wire. How much force is going to be on that wire? There's 2 wires and the mirror still weighs 20 pounds. So in our first example, these wires are holding 10 pounds apiece because the mirror weighs 10 pounds. Will a 10-pound wire still hold on each side? 10 and 10 make 20. Will a 10-pound wire on each side still hold this picture? No. No? What do you think it'll be? How strong does the wire need to be?
Stronger than 10.
Okay. And you got a guess? No, I'm not worried about the nail. I'm talking about the wire. I don't want the wire to break. Nail's massive. Huge nail. It's as wide as, it's as thick as my marker. I mean, it's not going to break. The anchor in the wall is not going to break. I just want the wire. How strong does the wire need to be on this mirror that's holding up this 20-pound mirror? So let's do this then. Let's say that this corner of the mirror, over here we said that if you put a cable there and just lift that side of the mirror up, it's 10 pounds. So there is a vector, and I'm going to kind of bring this out to have a bigger picture, but there's a vector over here that is, going to be, well, the gravity's pulling down, but we're holding this frame up on the wall. So there needs to be 10 pounds of force in a vertical direction to counteract the 10 pounds of force that's gravity going down. So we're going to have a vector going up that has a magnitude of 10. Because the corner of that mirror is 10. I mean, Joseph's answer over here is right. If this is the way we fashion our cables, 10 pounds, the whole thing's 20, 10 and 10 are 20, we're done. However, this is not the direction of the cable. The cable is pulling force over towards the anchor in the wall. And it's going over quite far. There's only a 10-degree angle here, not a 90-degree angle. The direction of the force is going from the corner of that mirror over to the nail, not in a parallel fashion, not parallel to the sort of gravity vector that is the mirror itself, which in total is 20 pounds. But we're just going to be talking about the left-hand side. So that's 10. We're not going to worry about that side. Okay? Well, so here's our forces. The force vector that we care about is the one that's representing the wire. And that vector has some component vectors in the form of A and B. So let's kind of bring this down and blow this up. We have a right triangle with a leg of 10. That's a vector with a magnitude of 10. And we have a vector which is the wire. So I'm going to do I'm going to say in blue we have vector W for wire, the wire vector. And I want the magnitude of that wire vector. right? The length of a vector, these vectors are directed line segments. The length of the vector represents what? The magnitude of a vector in this case is representing force. It's representing pounds. The example we did yesterday with the plane in flight, the length of the vector represented the speed of the plane, the speed of the wind, and the ground speed. Vectors represent forces in nature. At least that's one application of them. So we have a vector that is counteracting directly the gravity vector. We have 10 pounds on that corner. We don't know how long this hypotenuse is. We don't know how long this wire vector is, the magnitude of vector W, but we do know that the angle between the vector, the wire vector, and the frame itself is 10 degrees, which means the angle inside the triangle is what? 80. So from this acute angle inside the triangle, this 80-degree angle, we have a leg of 10 pounds, and an unknown hypotenuse. If we have the adjacent leg and we want to know the hypotenuse, so katoa, stop saying law of sine and cosine. We have right triangles now. Cosine. So now we have the cosine of 80 is equal to the adjacent leg of 10 over the magnitude of vector W. So that the magnitude of vector W, the wire vector, is equal to 10 divided by the cosine of 80 degrees. And that comes out to approximately, give me some calculator help. So let's round that up. Approximately 58 pounds of force. So when you come home, when you get your first apartment or place to live, or if you're decorating your own place, if your parents are letting you hang pictures on the wall, and you come home with a 20-pound mirror, and you want to hang that mirror on a single nail with your wire really stretched out horizontally, which is generally how pictures and mirrors are hung on the wall, that 20-pound mirror, you better be buying like a 60, 70, 80, 100-pound wire cable to hold that mirror up. Because there's a lot of energy that's being expended, a lot of force that's being moved in a horizontal direction to be able to support that vertical vector of only 10 pounds. I mean, I think that's rather shocking. In this scenario, to support 10 pounds, that cable only needs to hold 10 pounds. You have that cable go out horizontal, 10 degrees off of horizontal, and it's having to pull at a force of 58 pounds to hold up just 10 pounds of weight because of all the horizontal force. I mean, I think that's rather surprising. If I got some kind of 10-pound thing and I went to the hardware store, I'd assume a 20-pound wire is enough. It probably wouldn't be. That's your first example. Second example. You got 100 pounds on a ramp that is making an 18-degree angle from horizontal. How much force does it take to hold that 100-pound object from rolling down? Let's assume it's on wheels or it's ice. You know, there's like, you know, I'm not in physics, or, you know, we're not talking about friction coefficients. You know, this thing's on super awesome, you know, best rollers in the planet. They have like zero friction. That thing's 100 pounds. It's going to roll right down that ramp like that as soon as you let go of it. How much force does it take to hold that box there? That's a really good question, right? If you want to get this box, you know, if there's like some building here and this is a ramp to get into a building, if the box is 100 pounds and it's sitting on the ground and you just want to pick it up and put it on the floor of the building, how much force do you have to apply? At least 100 pounds. It's a 100-pound object. If you're going to just pick it straight up and put it on this floor, you're going to have to exert 100 pounds of force. There is a reason moving trucks have ramps on the back. To answer this question, or to be able to hold this 100-pound object still or get it to go up the ramp, you get to exert a lot less force than 100 pounds. Any idea how to figure this out? Let's start drawing some vectors on this. Can I draw a vector? How would I draw a vector that would represent the fact that this object actually weighs 100 pounds? What determines the weight on Earth? Gravity. Gravity. And where's the gravity vector go? Straight down. So we're going to draw a vector that is going to represent basically the weight of that object. So that vector, let's call it, well, I don't really need to name everything. I'll call it, this is vector v. This blue is vector v, and the magnitude of vector v is going to be 100. I need to create like a vector system down here that's representing what's going on. So I need to make a vector that is parallel to the angle of the ramp. So, you know, I'm kind of looking at this, and there's a sort of like this parallel line situation down here. And so along this parallel line, I'm going to say this vector here is going to be the force vector for the object. So let's call it B for box. Okay? That's going to be the vector that's holding the box. Now, in the diagram, where do I stop this vector? I want to have a third vector, which is how much force from this 100-pound box is going directly into the ramp. How much weight is this ramp holding? 100 pounds? So if an object weighs 100, the ramp is 100? Okay, let me ask you this. Here's my ramp. Here's my object. 100 pounds. That's not a very good ramp. How much force from this object is going into the ramp? 0. The ramp is the gravity is pulling down. If this is my ramp, the force going into the ramp is 0. If my ramp is also not really a ramp, but just a piece of wood, you know, held horizontal to the plane of the planet, and here is my 100 pounds, how much force is going into the 100 pounds? How much of my force is going into the floor, the ramp? 100. So if the ramp's horizontal, all 100 pounds of force is going into the ramp. If the ramp is vertical, which wouldn't make any sense in the real world, the amount of force from this box going into the ramp is 0. So if the ramp is at some angle, the angle of that ramp is going to determine how much force from the box is actually going into the ramp. The more horizontal the ramp, the more force is getting pushed into the actual ramp itself from the 100-pound object. So this ramp does arguably, except you're going to stand on this and probably hold it up, so, you know, but arguably this ramp does not, this line does not need to be strong enough to hold all 100 pounds of this force. But that vector that I'm trying to get you to think about is going to be perpendicular. So we need to have a perpendicular vector that is going to measure the amount of this 100-pound force going directly into this ramp. And this little blue, green, and red situation down here is what we're going to use to solve this question, which is, I didn't write it out, but you know, how many pounds of force will it take to hold this box stationary? This little red vector is parallel to the ramp. And when two parallel lines are cut by a transversal, the alternating interior angles are what? Congruent. So whatever this angle is what this angle is equal to. So this is the level ground, and even if it wasn't level, I'd be drawing a level plane here, or a level leg for the physics. We got a perpendicular situation. This is a right angle. This angle down here is 18 degrees, which I probably should have wrote smaller now. And that makes this angle 72 degrees. So that's 72 degrees. That makes this angle down here 72 degrees. And I don't know if we need it, but if this angle is 90 and this angle is 72 degrees, what little bit's left? Turns out to be 18. So if you do need it, this angle up in here is 18 degrees. I'm writing so small this hopefully shows up on the camera. We have a right angle down here. We have a blue vector, a blue gravity vector, a vector for the object, which is 100 pounds. This hypotenuse is 100 units long. How do we find the length of this red leg? How do we find from, you want to use the 18 or the 72? 18. So from the 18, we want the opposite leg, and we have the hypotenuse. What trig function's that? Sine. So to finish this up, we have the sine of 18 degrees is equal to vector b, the magnitude, excuse me, of vector b divided by the hypotenuse. So the sine of an angle is equal to the opposite leg over the hypotenuse. And the magnitude of vector v, the magnitude of gravity, the weight of the object is 100 pounds. So the magnitude of vector b is equal to 100 times the sine of 18 degrees, which means that the amount of force required to hold the box still is 30.9? Okay, I'm going to round it off to 31 degrees. So pounds, I mean. So approximately 31 pounds. It was 30.9 pounds. So 31 pounds of force is going to hold that box steady. And anything more than that, and you get to move that box up the ramp. Just for curiosity's sake, since now we know that it takes 31 pounds to hold this object still, anything more will move it up the ramp. So as long as you can push with at least 31.1 pounds of force, you can take that object up the ramp. You can lift it up with less than a third of the force than needed if you were to just pick it up. How much force is actually going into the ramp? We now know that the hypotenuse of this right triangle, that was the gravity weight, that was 100. We now know that the magnitude of b is equal to 31. How do we find the amount of weight that's actually going into the ramp? How do we find, let's say, the magnitude of vector r? And that's 18 degrees up here. No laws when you have a right triangle unless you like to make your life harder than it really needs to be. We want the acute leg and we have the hypotenuse. I'm not going to do that. I want to do trig. I feel triggy today. I want that adjacent leg and I have the hypotenuse. So whoop, whoop, cosine. Cosine of 18 degrees is going to be equal to the magnitude of vector r, the magnitude of the ramp, if you will, over 100. So the magnitude of vector r is equal to 100 times the cosine of 18 degrees, and that comes out to be 95.1 or approximately 95 pounds of force. So we now know how to hang pictures on a wall and calculate the strength of the wire you need. And we can move objects up and down and hold them still on a ramp.
Why can't you just solve for the weight of the triangle as the force, because it's the upward component?
You should ask your physics teacher about that. You probably could. But this, this is actually, the downward triangle that we're looking at is actually the forces as they exist in space.